Hi, my name is Chris, a postdoc and associated member of ML4Q, and you're listening to ML4Q&A, a show where members from the Matter and Light for Quantum Computing cluster answer questions about their work in the cluster, their research, and the future of quantum. In today's episode, I'm talking to Julian Schmitt, group leader of the junior research group Quantum Fluids of Light at the University of Bonn. Julian received the ML4Q Independence Grant and more recently an ERC Starting Grant. In 2022, he was awarded the ML4Q Young Investigator Award, honoring his contribution to the cluster's program, which specifically requires the collaboration between different sites. We talk about Bose Einstein condensates and the differences between the atomic and photonic kind. We recap how Julian got into atomic, molecular and optical physics, also known as AMO. In the AMO community, physics breakthroughs with relatively small teams are still possible. For example, the very first realization of a photonic Bose Einstein condensate that Julian was a part of. We chat about how optical quantum gases can shed new light on exciting open questions in physics such as grand canonical condensates and more generally the interplay between quantum physics and thermodynamics.
It is my pleasure to welcome Julian Schmitt to the ML4Q&A podcast. Really nice to meet you. We have not worked together and only met each other in the context of ML4Q.
Yes.
So in that sense, it's also a good way for me to broaden my horizons. So you work on photonic Bose Einstein condensates. And I think we should maybe first talk about what is a photon, then what is a Bose Einstein condensate, and then talk about your work. Does that seem like a plan?
That seems like a good plan, yeah.
So indeed, let's talk about what is a photon.
Yeah, first of all, hi Christian, also from my side. It's nice to be here. Yes, let's talk about photons. So essentially, I guess the low-level explanation of a photon is somehow that it's like the fundamental constituent of light, right? So it's the way we think about light is that it consists of energy packets that have energy that is basically determined by the frequency of the photon or by the wavelength, or even more like illustratively speaking, the color of the light. And we don't really know. If you look at the beam of light, for example, coming out of a laser, you don't really know where the photons are because they fluctuate around. They have certain photon statistics, and photon statistics is a very important aspect in general in our research field also. But yes, they basically these beams are consisting of many, billions and billions and even more particles of light, which we call photons.
Yeah, and you say statistics. It's indeed one thing to understand. Like for normal people, it's always light consists of these packets, and then it's all easy. But to be honest, in as a physicist, you probably have like at least half a year of lectures that explain to you how the statistics of photons work, because if you put more than one photon together, they actually behave quite exotically. So in the end, the concept that light is just made of packets sounds easy, but the reality of photons is actually quite complicated. How do you think about this?
Yes, I mean, I guess that's a very basic problem that we encounter very often in quantum mechanics, right? Quantum mechanics always appears, like, formally speaking, very simple. You have discrete states, discrete energy levels. You can hop from one state to the next state, etc. But then understanding and interpreting this and what it means really in an experiment is, of course, quite difficult. And for photons, I mean, you mentioned statistics. It's a super powerful tool for us to actually understand, is this state that we're looking at, the light field, is it actually completely classical, or is it completely quantum in some sense? So we just look at essentially, statistics, fluctuation properties. And that's also a very important part in some sense of the development, how we got from the notion, from the name photon to what we do nowadays, quantum optics, and using quantum optics even for quantum information science, etc. So statistics of a single light field is important, but also, of course, of some ensemble. Yeah? If you think of a gas of particles, and that's what we do with these Bose Einstein condensates, there you have also statistical distributions that tell you.
Yeah, I just find it fascinating. In principle, the photon, of course, in a sense, was invented by Einstein around 1905, but the theory of quantum optics then took another about 60 or so years to really come to fruition and for people to get to it.
Yes. Yeah, I mean, it's quite nice because it almost covers, or maybe even more than a century if you think about it. So I would always argue the first one to actually need the photon strictly for his explanation of a phenomenon to work was actually Planck. Because, yeah, it's also for my immediate work with photon condensates, the black body radiation spectrum, understanding why does the spectrum of the sun or a light bulb look as it does. He kind of postulated that photons should be energy packets, and he did not call it a photon.
Yeah. He also didn't like the photon, I think, at first, or at least he was.
Yeah, I mean, the first person to think about these light particles was Newton, right? Or maybe it was not the first, probably was not the first human being to think about light as particles, but he kind of, there was an entire century where people were quite happy of having gotten rid at all of this particle theory. You know, there was Huygens, there was everything seemed to work quite nice, double slit experiment, you have interference between waves, all these effects. And then suddenly there's Planck, who kind of needs the photon or the light quantum in order to explain the spectrum of the sun, which did not work before. Yeah? The Rayleigh-Jeans theory did not work. There was the calculations did not work out. There was this UV catastrophe. So it was, I guess, controversial even for himself.
Yeah, and it was definitely the start of quantum theory, and it's probably fair to say that studying photons and their behavior is really, in a way, has brought quantum theory forward. Like the community that has done the most to experimentally realize quantum mechanics for a long time was the spectroscopy community, which essentially worked with prismas, lenses, and optics. And of course, to study matter, but the toolkit is the toolkit of optics.
Yes. Yeah, I agree. This optics is maybe like as a tool has been around for such a long time and has been driving the exploration of quantum mechanics from the experimental side. I agree with you. At first, people were actually mostly interested in understanding how do the atoms look like, what are the spectral lines, and performing spectroscopy. But I think in the middle of the 20th century, we had like these experiments by Henry Brown Twiss, where they actually showed light has certain fluctuation properties. Then the invention of the laser obviously triggered a lot of further development.
And I mean, the work with single photons then also again was a completely different research field, which I guess started also I guess the coherent work with single photons and sort of quantum information with photonics is kind of later, right? It's really 90s, 2000s.
Yeah, I mean probably the first experiments where there this violation of Bell's inequality, that was of course a milestone. I mean, they received the Nobel Prize recently, right? So it has been recognized now, also officially. But also measurements of anti-bunching of photons and so on. I think that happened in the 70s, late 70s, 80s, during that time. That was, of course, like the first real strong evidence that light really consists of single particles. Everything before fluctuations and so on, you can also explain that actually with classical fields. But with this Bell's inequality violation, it really entered also quantum information science.
Yeah. So you would, I think it's fair to say you are, like as a physicist, you work with photons and optics. So the toolkit as an experimental physicist that you work with is this toolkit of quantum optics, right?
Yes, yes.
And so you are in this tradition that sort of, has really, like, I mean, it's like a more than 100 years of sort of very, very precise building of instruments. And
this is the strength of, I mean, we do experiments with photons, but we always see ourselves actually quite close to the AMO community, which is atomic, molecular, and optical physics. And of course, the strength of this community is having atomic physics around for 100 years. So you have extremely good knowledge of what you're doing. You can control atoms and matter using light. You can confine them, for example, and you can cool them. Yeah? You can prepare them in different states, create superposition states, things that we know from quantum mechanics textbooks. And yeah, so the experiments that I do are very much in the same breath.
So, okay, we talked a little bit about optics and photons. So, but what you guys do is you do Bose Einstein condensates of photons. So, let's first start with indeed what is a Bose Einstein condensate, and then maybe get back to the photons.
Yes. Yeah, so the Bose Einstein condensate essentially is a quantum mechanical phase transition of the Bose gas. And the Bose gas is a gas that consists of particles which have a very specific property, namely an integer spin. So they are unlike electrons, for example. Electrons, fermions, they have half integer spin. So if you take a gas of bosons and you put them in a box, then there has been a prediction again, like a long time ago, 100 years ago, in the 1920s, that if you cool them to low enough temperature, these particles that you would classically just consider to be individual particles which move around, they smear out. They develop some wave-like nature, what we call de Broglie wavelength. And these wave packets at some point start to overlap. That's at least the intuitive picture. Yeah, you cool them further down, the waves become larger and larger, and at some point you cannot really distinguish them anymore. And at that point, when particles become indistinguishable, you have to take into account the quantum nature of the system, and then let's say a macroscopic fraction of the particles in this gas really goes into the lowest energy state. And they there's like a phase separation. You have, on the one hand, you have the classical high temperature or high energy particles, and at the same time you have a macroscopic drop, let's say, of particles in the lowest state. That's why it's called a condensate. Mm-hmm. That's a phase transition.
The important feature of the bosons is that if you exchange two of them, the wave function doesn't change, right?
Mm-hmm.
And
the sign,
the sign of the wave function does not change. Indeed, it's kind of, you can really imagine, like when we write down the wave function, right? You can really imagine that we have to number the particles, but of course it shouldn't matter how we numbered them because we cannot distinguish them anymore at that point, mm-hmm. right? Is that the right picture for people to keep in their head? Like you have this soup of particles.
Yes, they all have the possibility, being bosons, they have the possibility to all go in the same quantum state, and in that regard, they all have the same set of numbers on them, like the same set of quantum numbers, which would not be possible with fermions. If I take a Fermi gas, it's not possible because I can only have one fermion
in
with
the same state.
Yeah,
and the bosons can all be in the same, and in the Bose Einstein condensate they are.
That's precisely what happens. Yeah, you get this massive occupation of one state.
So actually, exactly like in preparing, I also read a little bit about the history, and what fascinated me a bit was that originally people thought that this was sort of an academic curiosity, but that the Bose Einstein condensate would most likely never happen. Can you elaborate a bit on this?
I guess it's related also to the history of this effect, that you have a prediction from actually in terms of photons back in the day by Bose, who just thought of statistics. How can I distribute photons into different boxes? And then Einstein kind of realized that I can do the same thing for massive particles, atoms in this case, and then see that this follows a certain statistical distribution that undergoes this condensation effect. But then, in order to produce such a state, you need extreme conditions. Meaning, if you take an atomic gas, you require extremely low temperatures if you work with dilute gases. Okay, why dilute gases? That's what people do in the labs nowadays, or what they did for the first realization of a Bose Einstein condensate. You need a dilute gas because otherwise, if you cool it down, it just forms droplets or drops. It will form like
actually do the more classical phase transition of becoming a liquid or a solid.
Or a solid, exactly. So that's not what you want to do. You want to always keep this in the gas phase and actually allow the particles to develop this long wave-like nature. Yeah, this de Broglie wavelengths that I was talking about in the beginning.
Which means they need to be slow.
They need to be super slow, exactly. You need to cool them down in order to do so. And that was kind of like one of the major difficulties of producing a Bose Einstein condensate. So this happened 70 years after the prediction. Yeah, so 70 years. So we're talking 1925 to 1995. And you need to produce a gas at approximately 100 nanokelvin. The problem is, if you just use laser cooling techniques, you cannot get to these low temperatures because each photon that is hitting your atoms will actually heat them at the same time. And at some point, you cannot go to lower temperatures. And then there had to be like additional cooling methods.
I mean, to be honest, indeed, the community that makes the Bose Einstein condensates, I think today probably holds most of the temperature world records. And right, like I work in the solid state, and we are happy if we get to milli or Kelvin or maybe a fraction of a millikelvin, and that's sort of the limits that you can reach. Yeah. And here we're talking nanokelvin, or I think even less by now, right?
There are experiments where actually tens of picokelvins of temperatures are realized. Yes, it's of course the method that you can use laser beams to direct them at a gas of atoms, and these atoms then emit photons just into free space, and this energy is deduced from the system, and so you cool it down. Yes, it's so basically to this end. Yes, it's a very extreme state of matter. It's extremely cold, and maybe that was the reason why people in the first place were arguing, well, that's
never gonna happen.
That's very academic. That's very far away from any real implementation.
Yeah, but exactly. Nonetheless, people tried and succeeded. But you actually already in your master and now in your work as a PI, you work on even more special Bose Einstein condensate, namely those made of photons. So, what is the difference between a Bose Einstein condensate of photons and the Bose Einstein condensate made of bosonic atoms?
Okay, first of all, I don't know whether they are more special than the other Bose Einstein condensates, but
or at least it took even longer to realize them, let's say.
Yes, people actually never thought about photons being like massive particles, right? We know that photons do not possess a mass. And maybe that's already like indicating the difference between these condensates. So what we do using photonic gases and then making them what we call quantum degenerate, so we create condensates out of them, is that we first go into a lower dimensional configuration. We cannot do 3-dimensional condensates of photons because, again, coming back to black body radiation, if you cool down a thermal gas of photons in black body radiation, what happens? All the particles, all the photons,
vanish.
They disappear, right? So that's kind of a fundamental problem. So
Yes,
I cannot.
indeed. As you go to zero temperature, your photons just go away.
Exactly. There's this Stefan Boltzmann law that tells you you just basically cannot increase the phase-space density.
Yep.
But in our case, we throw away 1 degree of freedom. So we go from 3 dimensions to 2 dimensions, and this dimensional crossover allows us to assign again a mass to the photons. So this mass just is effectively an energy, right? It's like an energy offset that comes from this frozen out dimension. And so in that sense, the particles are much lighter, really,
compared to atoms. Yes.
No pun intended. They are really lighter compared to atoms, and that has some consequences for the experimental parameters where you can observe this condensation effect, namely the critical temperature, which is in our case room temperature. So that's of course a tremendous difference. You have 9 orders of magnitude difference between the cold atom samples and our photonic samples. And this is, I would say, probably one of the...
So exactly, we have ingredient 1, which was to reduce the dimensionality to give the photons an effective mass.
Mm-hmm.
What are the other difficulties that need to be overcome to make the photons more like atoms?
Yeah, so to make them more like atoms, you definitely want, so this Bose Einstein theory or the Bose Einstein condensation, that's an equilibrium state of matter.
Mm-hmm.
So you somehow want your system to be in equilibrium, in thermal equilibrium. And then you encounter problems with photons, right? With atoms, I guess everyone can understand very well that if 2 atoms see each other, they will collide, or they will
they bounce into each other.
They bounce into each other because they are massive. That should somehow there should be some interaction.
So we can have this picture of an ideal gas of, like, I don't know, ping pong balls in a that fly through a room and bounce into each other.
Exactly. Yeah.
But the photons, they don't bounce into each other because they don't see each other.
Yes, photons notoriously are known to notoriously not interact. So it's a very difficult endeavor actually to make them interact. Very active branch of science even nowadays as well. But you don't need to make them interact. Yeah, you just need them to thermalize. Yeah. So that again is inspired a little bit by black body radiation, where you have walls at a certain temperature which interact with your radiation field. Now just get rid of these walls and replace them with a material. For example, in our case, molecules. These molecules, they also can have they can vibrate, they can rotate, they have various configurations in which they can be in. So they can store temperature as well. And if your photons now interact with these molecules via absorption and emission cycles, then you can transfer energy between this bath of molecules onto the photon gas. And in the end, that can implement a thermalization process. And that's the second key ingredient.
And so essentially, you do need to choose these molecules and your photons to be a good match, right? Like the important thing is that the molecule can absorb a photon and emit a photon.
Exactly. So they have to be
of the photon that we are talking about.
Yes. But in principle, it's the material, the molecules that determine in which frequency range will your system actually operate.
Yeah, because indeed, you have a much more free, like you can in principle tune the frequency of your photons quite freely, but the materials that have the right properties are not as freely choosable. Like you can't engineer a molecule to have any sort of wavelength. Right.
So the material decides where we work at. One can say that. But you already mentioned that we can choose and change the energy of the photons. For that, of course, we have to say that how we actually contain and how we trap photons, because that determines also their energy. And for this, we use just mirrors, basically. something that is known in the field as cavities or resonators.
So indeed, to make the 2D, to trap the photons in 2D, you have two mirrors, and then the photons are trapped in between the two mirrors.
Exactly. And the spacing.
The spacing needs to be small compared to the wavelength.
Exactly, because if it's very large, then you don't freeze out, then you don't make them two-dimensional.
Yeah.
Really think of it as a photonic pancake, kind of like sandwiched between two super highly reflecting mirrors, not to lose any photons, etc., to really couple them well to the molecules, and the molecules also sit between these mirrors.
Yeah. So indeed, imagine a bathroom mirror where you can have these mirrors that you can rotate a little bit. You rotate them such that they face each other. You have the light trapped in between them, and there's this dye, right?
Yeah, and you can see nicely the back of your head.
Yeah, and so with these, I mean, of course, this is the mirrors that you have are quite they are specially made and specially coated, and the dye is specially chosen, and you have maybe some extra lasers that you shoot at this. So in the end, of course, the setup is not as simple as the bathroom mirror, but the idea is not in the end much more complicated.
The experiment really, at first sight, I would say, looks relatively simple, but it has, as you said, a lot of knowledge and many or deep insights were required to optimize the system really at the level, as you say. You really need perfect mirrors, you need the right emitter, etc. And that makes it experimentally quite challenging. Something that is very nice, though, what I maybe want to add here is, I said that the particles are non-interacting particles, but it's quite nice because in the context of Bose Einstein condensation, what Einstein and Bose considered in their early work, there were no interactions in these systems. This was
just
actually
temperature.
It was just having the statistical properties of, so basically it was just about having bosons and having them in equilibrium at a given temperature. They never talked about interactions. And so it's a really phase transition that is just driven by quantum statistics. It's not driven by any interaction effects or so. Of course, interaction effects might modify details of it, but at the heart of it, it's just from quantum statistics.
So indeed, let's now maybe switch gears for a little bit and talk about you, because I mean, indeed, the way that you got into this was you were part of this first demonstration in the way that we just described of a photonic Bose Einstein condensate in Bonn. And this was during your diploma thesis, before you started your PhD, right? So, I mean, I guess you studied physics in Bonn, and Bonn has had a strong quantum optics focus for a long time.
Yes.
Did you choose, at what point in your studies did you start focusing on quantum optics, and how did you choose this project?
Well, I would say that I got into the field of quantum optics already at the start of my master's time, when, as soon as I basically really started to understand atomic physics, I guess I was fascinated by it. And atomic physics and quantum optics, this is really just very, very close, these two fields. And I guess, yes, I mean, the field of photonics and laser physics equally was appealing to me. So I indeed did it was actually diploma thesis back in the day at the University of Bonn. And this topic was quite fascinating because I really liked the idea of lower dimensional quantum gases. I liked the physics of Bose Einstein condensation, which, as you remember, I mean, by the time was 15 years ago, the first realization of a Bose Einstein condensate. And then in 2010, we basically, I mean, I was really an undergrad student who was lucky enough to be part of this team and to learn about the ideas and concepts. And of course, when you have a new experiment, like a photon Bose Einstein condensate, it was actually the first realization of it. Then you have also many additional questions that follow up, like in particular for my PhD, what are the fluctuation properties of these condensates? Is there anything particularly interesting about them? That was how I kind of got into.
Yeah, so you definitely got in at the right time before it started to be cool, let's say.
Well, yes, I mean, I guess I did not really
realize at the time.
Yes, I was just lucky.
What's fascinating is, I mean, you guys wrote this breakthrough papers, and what for me as an outsider to this field, what's fascinating is the team is 4 people, right? Mm-hmm. And so this is the Weitz group in Bonn. I mean, it's fascinating to just have a breakthrough paper of something that essentially follows the ideas of Bose and Einstein about 100 years later, mm-hmm. And then have a team of 4 people to realize this. That to me seems quite special. How is it that because it seems like a small team for a breakthrough paper, right?
Yes, I mean, it depends a little bit on which field you're looking at. We did not require, for example, colleagues to produce samples for us. Mm-hmm. That already reduces the amount of authors. We did not have theory collaborators on this because in the end, it's ideal Bohm-Gas theory. So
indeed, your theory had been figured out before.
So exactly, in the end, it boils down to having really the creativity, the idea, and I would say the experimental and scientific rigor to really push this through such a project. And there, I think, in the end, of course, you also, even if it's just 4 people, you need, if it's the right 4 people to do it, then it can work. Nowadays, our publications, I would say, quite often actually have more authors, but I would not say that it's very unusual in the field of quantum optics to have really papers. Often the really like the seminal papers where some effect was demonstrated for the first time is often such that you only have a few authors.
I mean, I agree. Let's say, I mean, in most papers you have 4 authors who do the main work, and then maybe authors who produce the sample. Like, I don't want to minimize the work, but you have people who grow the material, who sort of do necessary steps for the mm-hmm. experiment, but who don't maybe perform the experiment themselves, and who also didn't design the experiment. So the team that designs the experiment and measures maybe 4 people is actually quite usual.
Yeah. And also we already had that the experiments are not super complex in the sense that you always need a team of 3-4 people to maintain them. Yeah. You can really do this in a team of 1 or 2. Let's say a team of 2.
Exactly. So I mean, but let's then talk about what made the breakthrough possible. Like we talked about the ingredients. We said we need mirrors, we need the dye, we need some optical table, and we need to be able to actually also image our photonic. Like what we didn't talk about much yet was that you also need to be able to sort of look at your photon gas, mm-hmm. right?
Yeah.
Like in any order you like. What are the technical challenges and sort of which ones are the ones that you solve in the lab, and which ones are the ones where you buy the right things?
Okay, maybe I want to go a little bit away from this original publication, because there, in terms of detection, it was pretty straightforward. We just had to do basic imaging. Go to
your later PhD work and so on,
yes.
where you did more detailed.
The challenge at some point is that we already mentioned that the photons, although they have a mass in our system, they are still very light particles. In other words, they move extremely quickly. Mm-hmm. So the timescales are very short. If I have a cold atom experiment, experiment, I can do things in microseconds to milliseconds.
Yeah, it's actually quite slow in a sense. That they are quite slowed down. And
that is the strength of the cold atom world, that you actually can capture all this with electronics really well.
But your setup needs to run for a few days to get the full image of what happens.
And it's not always in situ, etc. Yep. You have to repeat and repeat.
So in your case, the timescale is picosecond timescale?
Picosecond to nanosecond, exactly. In other words, it's quite demanding. You need cameras which are very fast if you want to see photon dynamics. That was important for my PhD, for example. I did Hanbury-Brown twist experiments, actually. I was looking for fluctuations of these condensates, and the fluctuation timescale is on the order of a nanosecond. Let's put it like this. So what you want is to
measure
record
faster.
Exactly. You want to sample this properly, and or look at dynamics. That was something else that I investigated in my work as a PhD student. That I kind of looked at some wave packets oscillating in the trap before it became a BEC, and that was 25 picoseconds. Round trip time in a harmonic oscillator. So for that, you need a big camera, you need a good camera, and this we cannot build ourselves.
No, of course you have to buy it.
So this stuff we really resort to the manufacturers who know what they are doing in that regard. But then, as I said before, the low-level stuff, spectroscopy, optical setups.
The dyes you also buy, right? But you choose.
We buy these dye molecules as a powder, and then it's our choice. How much do we use of it in terms of concentration? Okay. Which solvent do we use? Do we want something that evaporates immediately, or do we want something that is super viscous and will not evaporate in weeks?
So the spectroscopy work is also like, let's say you prepare your fluid with your dye molecules.
We have now our to-go solution, yes.
Once you find it. But exactly. You needed to, one part of the experiment is you need to find the right solution.
Yes. And then you want to characterize it. You want to see what is your absorption spectrum, what is the emission spectrum, because that depends on the solvent that you use as well. And you want to know what is the quantum yield. This has to be really high. We want to always be very close to 100% quantum efficiency.
Which means that photons don't get lost. They just get absorbed and emitted, but they don't disappear.
Right. So basically, there's just a little bit of energy taken away or added to a photon, but it's not taken away entirely, such that. Yeah. Yes. And
the mirrors you also buy.
Mirrors are kind of like a hybrid solution of components are bought. Then, together with manufacturers, we have a custom design. That also allows us now to go to more fancy traps or containers, cavities essentially, as compared to this very early work.
Because the key is that you can actually structure, right? You can make structures on the surface of the mirror.
Let's call it, maybe we can structure the mirror.
Oh, you can structure the mirror.
It remains a mirror. It keeps its high reflectivity, but it's really that your cavity becomes transversely, let's say, the cavity length varies.
Yeah, and so essentially you have these photons that are trapped in 2D, but now in this 2D they actually have an environment like a box or multiple, like you can...
lattice type of structures any kind of like ring shapes or... we don't really work with any kind of pictures of someone, but we are interested in using these systems to understand states of matter that are maybe a bit more complex now. We don't want to just look at a single condensate, but maybe like connect 10 of them or so in a coherent fashion, and then use this to...
we skipped a bit through we talked that in principle, so you were part of the initial experiment, you did your PhD exploring this further, and then you did a postdoc, and now you're back as actually a principal investigator. So we're actually talking about, this is your current passion. You're still working very hard on using the system to explore new physics and So indeed, we talked about most of the components by now, I think, but there's still a lot of creativity you can put into it. Is there so indeed you can with the right camera you can in a time resolved way image the fluctuations of the photons. Is there still a lot of extra accuracy in time or in space or so that you guys can still get there, or is it more that you want to work more with structuring the mirror, or work more with changing the dice and changing the physics of the system? Where are the ways that you can still explore the system there?
Yes, I think there are many ways to explore the system further. Several of them you just named. Definitely creating and being able to control larger, let's say, lattice systems, coupled systems of these condensates. Implementing this is a challenge because we need to be super precise in putting each of the small micro wells in which the condensates are trapped. Need to put them on resonance. That's a challenge. This needs to be. This is what we are working on at the moment. At the same time, of course, exploring new emitter types, new materials, and also possibly nonlinear materials, such that we can have photon-photon interactions in the system. So basically, bring interactions back. All these are open frontiers, and we are working on various directions there.
Do you already get the photon-photon interaction by just making the solution more dense? Or what is the right way to, what you need is a molecule that, you never get a direct interaction. So you have a molecule that absorbs one photon and...
Yes, well, you can also think of having a direct interaction if you have a nonlinear medium. Let's assume that you put on one of the mirrors, you put a little bit of a coating with material that has a Kerr nonlinearity. That basically means if a photon is propagating in this medium and there is a second photon,
it changes.
It will change the refractive index, right? And that will change the energy of the particles at this position. But of course, you can be creative here and also think about the saturation effects. Like I think you were just alluding to. So you have a photon which hits a molecule, and then this molecule is busy, right? It's excited, so the second photon does not cease. But currently, our experimental parameters are in a regime where this is not at all the case. There's always a second molecule and always a third molecule that can absorb the photons coming in. These would be, for example, what you just mentioned, would be some saturation effects.
Yeah, one thing in addition that we should mention about this work, which I we did say in your PhD, indeed you worked on the statistics of this. And one curious thing about the photon Bose Einstein condensate compared with the atomic Bose Einstein condensate is that one is in the microcanonical ensemble and you can be in the grand canonical ensemble. Can you elaborate a little bit? And maybe we have to explain to our listeners.
Well, don't you remember your thermodynamics and statistical physics textbook? Yes, of course. This is a very unusual scenario that we can realize here. It's, of course, very interesting because it's difficult in other platforms. It means essentially, is your system that is made out of photons, is it isolated from the environment, or is it allowed to exchange energy or particles with some reservoir? And for cold atoms, I think it's easy to see. This is a system that is in vacuum. There are maybe some thermal atoms in the excited states, which can act as a small reservoir, but this quickly saturates. For us, this is a bit different because we have photons being in the condensate, and at the same time, they coexist with molecules. And these molecules can be in an excited state. And if you now think of having many of these excited state molecules, these act like stored photons in a reservoir that can be retrieved and go into the condensate, and at the same time the condensate can reduce its number by being absorbed into this reservoir. So this coupling, and this is something that is actually written down in every statistics book or statistical physics book, you will have strong fluctuations. You will have strong number fluctuations in this mode. And that's quite interesting scenario. Imagine you have a system consisting of 100 different modes. Each of them is fluctuating. That's no problem because all of the modes are fluctuating in an uncorrelated way. On total, this system will never show strong fluctuations. But for a BEC, it now becomes very interesting because suddenly you condense, and now I have, let's say, 50 or 70 or 80% of the particles in the ground state, which is a single mode, and this thing fluctuates strongly. So I can go even to absolute temperature T equals 0. Okay, that's at least theoretically, almost. Yeah. And then I have a macroscopic condensate which still fluctuates. So it's kind of counterintuitive phenomenon because you go to
you have quantum fluctuations at 0 temperature.
Yeah, exactly. Reservoir-induced fluctuations in particular. And this is something that we were able to observe and also control during my PhD work. And it's also a very strong asset for future work. So we are trying to implement and use this for novel studies in more complex lattice type system.
Yeah, maybe I should you have this very powerful platform where you can explore exotic physics that, as we said, had not been observed before. But is it that, how do you think of this as realizing new physics in its own right? Or do you also think of it as a quantum simulations platform where you try to imitate another system in a maybe more controlled way, because the control that you have is maybe better than what people have in a solid state?
So currently I would not say that this is really at the level of being a contester or competitive quantum simulation platform, but you can use this system to understand other materials, and you have novel tuning knobs and let's say much better insight, also analysis tools. I mean, optics and photonics has great analysis tools. Imagine you can create a lattice of photon condensates, and which you can, by doing the proper mapping, this actually looks a little bit like a system out of many different spins which are coupled. Now you can start asking yourself the question, what happens if I take out one of these condensates? I don't allow it to be there, or I detune it, so I create somehow disorder in a controlled way, and I see everything. I see the phase, I see the number of photons, this is very similar to superfluids in ultra-cold atoms, or even in solid-state physics, where you have these XY models. So I think there's a lot of potential for also simulation and complementary insight for other fields.
If you want to now have differently structured mirrors, how quickly can you change them? What is how easily how easily adaptable is your setup? Because, for example, optical lattices are one of the big simulator platforms, right? And they are quite perfect. But if somebody wants to go from a lattice with triangles, from triangular to a square lattice, that's like 2 PhD students. And
yes,
in sort of in time and money.
Good PhD students.
Yeah, exactly.
Yes.
How is it for you guys? How much work is it to adapt these things in the system?
I would say the flexibility of our approach to realize lattices or any kind of structures in the cavities are the flexibility is very high. So we can choose to make, instead of a regular lattice, as you would create with interfering laser beams, we can choose to make alternating hoppings or variable hoppings, or place the condensates at different transverse positions on our cavity mirror. There we are extremely flexible. Since we do this lithography method basically in-house. We just go from one lab where we produce the mirror to the next lab where we put this mirror into our cavity and assemble the whole thing. The ways of producing it it's fairly fast.
So like weeks rather than...
I would say an hour.
Yeah.
Something like this. You take your mirror, you put it in there, you scan your laser beam, you write a structure, some lattice type structure. Okay. You take this mirror out, you put it in your microcavity system, you assemble
your
it.
measurements are even also very quick, right? Like
you have, of course, you have a repetition rate of 100 or 200 hertz or so. During that time, you get long 1 microsecond of photon evolution, so where you can do all the stuff. So you have the data rates are incredibly high. It's quite nice.
So essentially, if somebody comes up with the right idea, in principle, it can be done in a time scale of a month or two, including everything. Like,
yeah, of course, the devil is in the detail.
Because
you always have to
your
do
initial
some
idea
debugging.
is usually not completely right.
Yeah, exactly. Or something is not properly working. That happens, of course, most of the time, and that's also what is part of doing research, I guess. There are certainly also some limitations that, of course, I told you it's very flexible, this approach, but we cannot easily, for example, change a potential, for example, on the timescale of the photons, right?
No,
photons,
exactly. You have to work with the static.
Yes.
Currently, you have to work.
But even there's room again for novel ideas and novel experiments, and I'm pretty sure also there we will see in the future tools to be able to drive condensates on these timescales, or to quickly turn on the coherent hopping and turn it off again. This can be done, but again, then we are more on the timescale of a full PhD.
I see.
So whenever you explore something new, it's.
But anyway, it's really a new fascinating platform. And the other thing is, in Bonn, like the community of people doing what you are currently doing is not very large, right? Like, so you're not like hounded by the competition to get to the next result, because this sort of photonics that you do is not a big
Yes, well, there is not the direct competition for sure in Bonn. There's no direct competition anyway, but overall the entire research landscape, there are a handful of groups working with these systems and exploring the new things in this matter. But there's not too much immediate pressure. We need to be the first to do this now. But we have quite a lot of overlap with also the fields of atomic physics. We learn a lot from atomic or cold gas physics, but the other way around, maybe they also learn some things from us. And it's very similar with the field of exciton polaritons, which is very close to solid state physics.
Yeah. All right. Last personal question: when you learned quantum mechanics, when you studied physics, did you prefer quantum mechanics or statistical physics, or was it really both?
Well, it depends on the point of time, I have to say. I would say, looking back, I would say that quantum mechanics is pretty strong and pretty good and pretty cool. But at the time that I was learning it, I think I did not really get the message of it. That was why I was so happy about atomic physics, because atomic physics gave me a reason why we need quantum mechanics. And statistical physics, I'm always amazed by how much people knew already 100 years or 150 years ago. I mean, Boltzmann, what he calculated, all these things. It's and there are so many things to also still look for in statistical physics. So I find it's both. Maybe it's not even comparable. It's both in its own right. Excellent or nice disciplines or sub-disciplines.
Yeah. So thanks a lot for coming on the podcast, and
thanks for having me.